Hi, what I have here on the workbench today is a FNIRSI LC1020E LCR meter. On this channel, I have reviewed quite a few LCR meters before, and this one is actually one of the cheapest ones by far. It is retailing for some $60-odd. So in this video, let's actually take a look at whether or not this meter is something worth your consideration. Banggood provided me this meter for me to review, and as usual, I'll leave a product link in the video description below for those who are interested in getting one after watching this video. Before I get into the review though, let me briefly tell you about today's sponsor, NextPCB. Want to bring your electronics projects to life with speed and precision? With NextPCB, turning your designs into professional circuit boards is simple. From FR4 to aluminum, copper, flex, and rigid flex boards, NextPCB has you covered, with up to 32 layers for even the most advanced designs. Beyond manufacturing, NextPCB also offers turnkey assembly services, so you can go from design to a fully assembled board in just one place. Getting started is easy. Just upload your Gerber files, select a few parameters, and you're ready to go. You can even add stencils to make assembly easier. With fast turnaround and reliable shipping, your boards arrive when you need them. And to make it even better, your first order comes with $20 off. Try NextPCB today by following the link in the video description below. Now, from a glance, it pretty much looks just like any other modern LCR meters. It's actually quite light. Now, that's not surprising, as the main functions are handled by a microcontroller. Of course, we'll have to take a look at that towards the end of the video in our teardown. FNIRSI also provided these Kelvin clips for 5-wire measurements. It is essentially just 4-wire Kelvin sensing plus the guard terminal here. Now, there are a couple ways guarding can be implemented. One way is to drive the guard via a unity buffer to the same potential of the signal wire, so that there's no leakage current flowing between the conductor and the ground. This technique effectively removed leakage resistance and stray capacitance from the measurement. I did an entire video on guarding and why it is important. I will leave a link here if you wanted to dive deeper. Anyway, another method of implementing guarding is tying the guard to a potential that is different than the instrument ground. And through calculations, you can remove stray capacitance and inductance. I'm not going to dive into the details, but I will provide a link to the theory behind that in the video description below. Let's actually take a look at the supplied Kelvin clips again. You can see that a significant portion of the cabling is actually not covered by the guard. So this could potentially reduce the measurement accuracy. Now, there's a trade-off with practicality, of course. The supplied Kelvin clips strikes a good balance, in my opinion, as when you take a look at the clips supplied with my other LCR meters, you can see that the shielding goes too close to the clips, making measurement a little bit more difficult, especially if you're trying to, for example, click something up very close, and you can see that they don't spread very far apart. So from that regard, the supplied Kelvin clips with the 1020E actually are quite easy to use, as you can see here, so that's a good compromise, in my opinion. Of course, you don't have to use the Kelvin clips to do your measurements if you don't require maximum precision. You could just use the banana jacks. For most of the LCR meters, manufacturers typically provide you with these kind of banana to alligator clips as alternatives, but these are not provided by FNIRSI. They simply just provided a set of multimeter probes as alternatives. So for today's testing, I'm not going to use these. I'm just going to use the provided Kelvin clips. Coming in the product box, you also get a short adapter for calibrating your unit and also a USB cable for connecting to the computer and charging. And before I power it on, I just want to quickly show you the specs printed on the box here. And this is the product box. And you can see at the back here, we have the specs. You can see that test frequency can go from 100 Hz to 100 kHz in these steps. And the basic accuracy is at 0.3%, which is not bad at all. The measurement range for inductance can go up to 100 henries, for capacitance up to 100 millifarads, and for resistance go up to 10 megohms. And also you can apply bias up to 0.5 volts. So we'll take a look at that later. All right, let me plug in the Kelvin clips and we can do some measurements. And by the way, the quality of these clips are actually quite good. As you can see here, they slide in and also we can lock them in place. You can see that now it's very secure. Actually, before doing any measurements, let me briefly show you the measurement waveforms on an oscilloscope. Let me stand it up here. So you can see both the oscilloscope and hopefully the screen of the LCR meter. Let me power it on. And we power it on right away. Okay, so let's actually measure the output waveform here. Let me acquire a signal. You can see that just like all LCR meters, it uses an AC signal for the measurement. And of course, we can adjust the frequency and amplitude. So let's give that a try. So let's change the frequency here. So right now we're at 100 Hertz, 120 Hertz, 1 kilohertz, 10 kilohertz, and 100 kilohertz. Let's try it again. Yep, indeed. Right now you can see here the frequency measured is 100 kilohertz. So let's go back to 100 hertz. And let's change the amplitude here. So we change the level. Yeah, you can see that we're now at 0.1 volt, 0.3 volts. You probably have noticed that we also have this bias parameter here. Currently it's set at 0.5 volts. And this is actually useful as it will give you better accuracy for electrolytic capacitor measurements, as those are polarized. The bias voltage can also be adjusted. Let me just show you that. So let's go to bias, and we can adjust that. Right now it's 0. You can see that we get a AC signal. And of course, we can choose between 0 volt and 0.5 volts. Now let's actually take a look at the guard implementation here. So for that, I plugged in these two alligator clips you can see here, and one is in the guard terminal. So let's take a look at the waveform here to see whether or not it is driving to the signal or it is actually driving close to the ground. And then you can see that it's actually driven to about minus 200 millivolts, and that's a DC signal. So let's actually change the different range to see if it impacts that. Nope, it doesn't. So it looks like it essentially is a fixed voltage. And this essentially is the second technique that I mentioned, how guarding is typically implemented. All right, let's start with resistance measurements. I'm going to verify the results with the Zoe DQ02 I just reviewed not too long ago. The first resistor I'm going to measure is this 100 ohm 0.1% tolerance precision resistor. By the way, all the conditions, I'm trying to set those the same between these 2 meters. You can see here the frequency is at 100 hertz and the level is at 0.6 volts. So those are the conditions we could be measuring under. And you can see we're measuring roughly 99.95, no problem. Let's use this to measure. By the way, this is what I was mentioning earlier. You can see that the cables are a little bit short, so it's a little bit difficult to measure here. And you can see that we're getting 99.94, 95. It's pretty much the same reading. So that's not a problem at all. Now let's try a different resistor here. This is a 1.25K. And indeed, it's 1.25. And by the way, of course, the readings will be influenced by the measurement frequency. For example, if I change the frequency here, and in this case, you can see here, especially when we're changing to higher frequencies, the measurement is significantly different. So let's go back to 100 hertz. Let's verify that. And no problem. Of course, we can change the frequency on this one as well. 120 hertz, 1 kilohertz, 10 kilohertz, and 100 kilohertz. Now, interestingly, the 100 kilohertz measured on this Zoe is still 1.24K, whereas we measured on the FNIRSI became 1.1. So that's very interesting. Let's try that again. Let's try the frequency here. 1 kilohertz, 10 kilohertz, 100 kilohertz. Yeah, so definitely there's some discrepancy between these 2 meters. Unfortunately, I think the problem is actually with the 1020E, because this is a very stable resistor, it's a high precision resistor. Even with 100K, of course, we're expecting to change a little bit, but not by that much. And now let's take a look at a 1 mega ohm resistor. And you can see that we're measuring 0.985. How about the Zoe? Yep, no problem. One thing I just noticed, is that on the 1020E, we don't have the ability to select whether or not the measurement is in parallel or in series. That's actually very interesting, as series mode is typically used for low impedance measurements, such as measuring small resistance, small inductance, and large capacitance, whereas parallel mode is for high impedance measurements, such as large resistance, large inductance, small capacitance. On the DQ02, you can see that we can actually select whether or not we want to do parallel or series measurements. You can see here we have a mode. Of course, it's spelled wrong. It says model. But anyway, here you can press and you can change it to series measurement, parallel measurement, and automatic measurement. In this case, it's doing the series measurement. But we don't have that option on the LC1020E. So in my opinion, even if the FNIRSI is actually doing the automatic measurements, selecting between series and parallel, it should indicate on the screen here. Anyway, something for FNIRSI to improve in the future if they are listening. All right, now let's do some capacitor measurement. And first, let's start with a small capacitor. So for that, I'm going to select capacitor and I'm going to change the frequency. Let's do frequency here. Let's do 100 kilohertz because it is a 10 picofarads capacitor. And by the way, I forgot to show you, of course, I can also change the update speed. Right now it's at slow. And when it's slow, it's actually going to give you the better accuracy. Of course, you can change the speed to medium or fast. So let's actually start with fast to see if we can measure the 10 picofarads capacitor. It's measuring 8.3 and it's fairly stable. I don't think the speed will impact the reading here. No. So let's do the fast here. And also, I'm going to change the speed to fast on the Zoe as well. And let's change it to capacitance measurement. Now, the measured capacitance value on the Zoe is 14.5 picofarads, which is significantly different than what we measured on the LC1020E. Let's actually do that again. Yeah, you can see that we're still measuring 8 picofarads. And I'm going to bring in a third meter momentarily to double check the value. But right now I can show you that also you can change the secondary display. Right now we're displaying dissipation factor. Of course, we can change it to Q factor. We can change it to angle and series resistance, so on and so forth. All right, so I brought in my Handtech 1823C as a tiebreaker. And you can see that we're measuring under pretty much the same condition. In fact, right now the level is different. So let's change the level to, let's see, 600 millivolts. And yes, the result is around 12 picofarads and is significantly higher than what is measured on the LC1020E. So I would say in this case, the results measured by the LC1020E is not as accurate. And I just dropped the frequency to 10 kilohertz. And let's use the 3 meters to read this 10 picofarads capacitor again. You can see that we're reading roughly 9.5 on the FNIRSI. And let's try the Zoe. Now it's actually much closer, 10.7 on the Zoe. How about the Handtech? $11.8. So yeah, so there's still quite a bit of discrepancy among the 3 meters here. All right, now we're measuring a 100 nanofarads capacitor with the LC1020E. You can see that the series resistance reading is jumping around, and let's actually change it to slow here to see if that is the problem here. Okay, we change it to slow, it is still jumping quite a bit. So let's verify that with a DQ02. And I'm going to change it to slow too, just so that the conditions are the same. You can see that the measured series resistance is quite different than what we got on the LC1020E. And this again is the same capacitor confirmed by the Handtech. And you can see that the ESR measurement is very similar to what we got on the ZT-DQ02, but the measured result is significantly different on the 1020E. So from the tests done so far, the 1020E, the measurement is not as accurate. Now you're looking at the measured result of an 820 microfarads capacitor. You can see that we're getting 832 with an ESR of 0.04 ohm. So let's take a look with the Zoe. And on this one, it's actually very similar. Of course, we can change the bias voltage. Now, I don't think we're going to get a much different reading here. So let's go back here. Right now, the bias voltage is 0. So let's change it. Let's see if we can change it to 0.5. And the result is pretty similar. Let's do the same thing on the Zoe here. Now I have set the Zoe to be exactly the same with 0.5 volt bias and 0.3 volt level. So let's see here. Yeah, I think the results are actually much closer now between these two meters. And the last capacitor I want to try is this large one, is this 15 millifarads capacitor. And let's give it a go. And you can see that we're measuring right around 30 millifarads with a series resistance of 0.016 ohms. So let's actually verify that with the DQ02 under the same conditions here. Yeah, these connectors are not as convenient as the other ones. Give or take, I think the results are very comparable. So it does seem like for larger capacitors, the accuracy of the 1020E is actually pretty good. But for smaller ones, it is a little bit off. Now let's actually take a look at the inductance measurement. The first inductor I'm going to measure is this R50, which is a 0.5 microhenry inductor. So let's first take a look with the LC1020E. And by the way, I have changed the measurement frequency to 10 kilohertz. Actually, let's do 100 kilohertz. Let's do 100 kilohertz. And I'm going to set the same thing on the Zoe as well. So let's take a look at the measurement. And we're measuring 0.5 microhenry, which is pretty much spot on. Now let's try the Zoe here. And in this case, the Zoe measures 0.6. But again, the Q factor actually is quite different. You can see here, this one measures 75, 76, whereas I think we got, I don't know what we got here. Let's take a look again. The Q factor we measured on the LC1020E is only 3. So clearly, one of these is definitely way off. Again, let's actually verify that with the hand tag. All right, moment of truth. You can see I set it to 100 kilohertz and level is 600 millivolts, exactly the same. So let's measure the same inductor here. And you can see that we're measuring 0.6 microhenry and the Q factor is 80, which is much closer than what is measured by the DQ02 compared to the 1020E. All right, I can be sitting here doing measurements all day, but let me measure another inductor, and this time we are going to measure a slightly larger one. So let me drop the frequency to, let's say, 10 kilohertz. And this is the inductor we're measuring. So on the LC1020E, we're measuring roughly 1.2 millihenry with a Q factor about 23. So let's remember that. And let's switch it to the Zoe. So let me actually drop the frequency to 10 kilohertz. So the conditions are exactly the same. And you can see that the inductance reading is actually pretty much the same, but the Q factor is significantly different. So let's actually verify that with a hand tag. So for that, I'm going to change the frequency back to 10 kilohertz. And again, you can see that the Q factor measured by the Handtech is very similar to the Zoe, but definitely is different from what is measured by the 1020E. All right, now let's open it up and take a look inside. Before we look at the circuitry here, let's actually take a look at the power consumption. The battery here is a 3 amp hour battery, so let's take a look at the current here. And I'm just going to use a clamp meter so that I don't have to desolder anything here. Let's power it on. And you can see that it's drawing about 100 milliamps. So that's actually quite good. Let's change the mode here. I don't think it's going to be impacted. Nope. Okay, so given this meter can actually run for about 30 hours before you need to recharge. Very good. And I also just removed this input board. You can see that the design is actually quite modular. It's very nice. It plugs in to the main board here. Anyway, so here is our guard, and here are the 2 inputs. And you can see the traces in the back. And here's a close look of the main circuit board. Everything is pretty much what I expected. As you can see, we have a charging controller here, a buzzer here, and this is our main microcontroller. Unfortunately, just like most of the cheap Chinese meters I have reviewed recently, the markings on the chip has been erased. I guess I really don't understand why they keep removing the markings. But other than that, there's not really a whole lot going on here. On this board, you can see we have quite a few of these RS-822 op-amps. These are just your run-of-the-mill op-amps. And up here, we have a CH444G, that's a digital switch. And here we have a RS-8752, that's a slightly higher bandwidth op-amp. And that's pretty much all there is on this board. And by the way, if you look up here, you can see we actually have these 2 openings here. So this case is actually used by multiple devices, including some of the oscilloscopes. Overall, this is just a very cheap LCR meter. Anyway, I hope you enjoyed the video. If you liked it, please remember to give it a big thumbs up, and don't forget to subscribe to this channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.